Hello, calculus students. Using integrals to find area between curves. Let's begin with two different scenarios in which we are working with vertical strips to find the area versus horizontal strips. When your curves are defined left and right by vertical lines, so vertical line. So this is some sort of x-coordinate, like x equals a, and then some other x-coordinate that's larger, x equals b. And then your upper boundary is just given by some sort of function. Let's say that this is y is equal to f of x. And then the lower curve will say y is equal to g of x. The idea here is to do lots of skinny rectangles. And the more rectangles you do, the better the approximation. But to set up an integral here, you imagine one example of a rectangle through here, and you figure out its length and its width. Its width will be change in x, so delta x or dx, and its length, or its height, is going to be the upper y-coordinate minus the lower y-coordinate. In other words, you could do the upper function minus the lower function. And first of all, the area of just that strip is going to be the length of the strip, which is upper function minus lower function, times the thickness. We'll use the dx differential for the thickness. And then you sum them up. Here's our big S, integral. Sum them up from x equals a to x equals b. And this is the setup for the area of the region. Now, if your region is on its side and instead you have horizontal lines that are defining the top edge and bottom edge, so we have some sort of y-coordinate, y equals a is the lower, and then a y equals b, some larger y-coordinate, which is above. And you have a function over here on the right. But notice that this curve over here on the right is not a function in the sense of y being a function of x, because it fails the vertical line test, right? There's multiple y-coordinates for a single x-coordinate, potentially. But it is a function of y. X is a function of y, meaning if you do a horizontal line test, you'll never cross this curve more than once at a time. X is equal to some function of y. And then the curve on the left will be x is some function of y, some g function of y. And we do horizontal strips in this case here. So imagine some horizontal strip here. Its length is going to be the further right x-coordinate minus the furthest left x-coordinate. So we would do f of y minus g of y. And its thickness is the delta y. So the area of just that one strip is f of y minus g of y times dy. And then if you do an integral and add them all up from y equals a to y equals b, you get the area of this region, but using horizontal strips. In words, it's probably best to think that when you're realizing that you have a situation like this first case here and you're going between two functions of x, instead of using f and g and memorizing something like this, it's better to think upper function minus lower function. And notice everything here is in terms of x. Like these are functions of x, this is a dx, and these are x coordinates. But when you're working with functions of y, you have everything is in terms of y. And the limits of integration are y coordinates. These should be functions of y, and you have a differential dy. Here in this case, you want to think right minus left. Okay, let's put this information to use. Find the area of the region or regions bounded by the curves. Now there are 4 curves listed here. So we've got the red curve is the first one. The blue curve is the line 6 minus x. The vertical line, x equals 0, is this green line. And then x equals 10 is the purple. Now we are expected to find the area of the regions bounded by the curves. So we are trying to identify what regions exactly we are after here. I'm going to shade in using gray. And you should only shade in things that actually use these curves that are mentioned in the list. So for example, I wouldn't want to shade something like this and say this is what we're after, because this region I just shaded uses the x-axis as part of the boundary. However, the x-axis is not mentioned in our list of boundaries. So we have to avoid shading anything that uses as part of its boundary something that's not in this list. So what we're going to be after here is the area between the green, blue, and red in this triangular region right here. And then there's another region that uses another 3, this other triangular portion over here. So once we identify the region or regions that we believe is bound by the curves, then we can go about trying to find the area. Now, one key thing that needs to be done is recognizing that looking at the region here on the left, the upper function is blue and the lower function is red. But for the region over here on the right, the upper is red and the lower is blue. So there's a transition of which function is considered the upper and which function is considered the lower. This is going to require us to split our problem up into two integrals. If we're doing this by hand, we're going to want to figure out where they intersect. And by where, I mean which x coordinate. Now in this visual, it looks like it's happening around 4, but to confirm that, you actually want to set these two functions equal to each other and solve for x. We'll take the red function, which is radical x, and set it equal to the rule of the blue function, which is 6 minus x. And you can see just by plugging in 4 that 4 is the solution of this. But if you are to try to solve this by hand, you would want to square both sides next. So square radical x, you get x, and then square 6 minus x. Now be careful you just don't distribute the square and do 36 minus x squared. You're going to have to FOIL to continue to solve this. We have 36 minus 12x plus x squared. Then I want to subtract this x over to the other side. So we get a 0 on one side, and I'll rearrange the order over here. We have minus 13x plus 36, and then attempt to refactor this. Hopefully it factors. If not, you have to use the quadratic formula, but knowing that 4 is an answer tells me that this should factor with x minus 4 being one of the factors. The other factor is x minus 9. So you seemingly get two answers out of this, 4 and 9. But if you look at the image, over here is where 9 is at, and the red and blue do not intersect. However, if you were to change this equation to x equals y squared, it would actually be a complete parabola, and you would see a second point of intersection over here. But for the purposes of this task, 4 is the only valid answer that we're after here. Also recognize that vertical strips are how we wanted to do this. In fact, that should have been the first assessment I made here, is if you imagine a vertical line that you move across this function, notice that the whole way across the region, this vertical line, as far as the gray region is concerned, it's the same curve defining the top and the same curve defining the bottom. It's always blue above red the whole way up until 4. But then after 4, these vertical lines, it's always red on top and blue on the bottom up until the edge. If I had done a horizontal line, you would notice some issues as you try to integrate across this region. Right? So think right minus left. Right is purple and left is blue. And as you integrate up, right around here, we get a transition because these horizontal strips, right is purple but left is now red. And so there is a transition that happened at that point of intersection. We would need an integral for this piece up here and then a separate integral for this piece down here if I were to use horizontal strips. Looking over at this region, similar issue. Right is red, left is green, and that's true up until right here. So we need one integral for this first part if I'm doing horizontal strips. From this point up, right is now blue and left is now green. Right? So we would need an integral and an integral, and then an integral and an integral to get this answer using horizontal strips. Vertical strips are much easier in this case. We have two different regions. Let's call this region 1, so A1 and A2 is what I'm after. Area 1 will be an integral, everything in terms of x. You know, x equals 0 is the green line, so we go from x equals 0 up to x equals 4. And then we set this up so we do the upper function, which is the blue, and we do the rule for it. So the 6 minus x is the upper function. We put that in parentheses, minus, and then we do the lower function, which is red, which is radical x. And then you can put that in brackets and then put the dx. Now, very often, if you look back at these general formulas, these brackets aren't written because it's sort of implied that whatever's between the integral sign and the differential is nested in the implied set of brackets. Similarly here, you could, in theory, just leave them off and then integrate that function. We could integrate this one by hand fairly easily. I'm going to use Desmos to do a lot of my integration in today's lecture. You can go to Functions and go to Miscellaneous and touch that integral sign, or you can, if you've got a keyboard, you can just type in int, it makes an integral. Anyway, we're going from 0 to 4. And for Desmos, you should put the integrand in parentheses. And inside that integrand, we had a 6 minus x, minus, and then we had a square root of x is the second function. And then the differential, type it in dx outside the parentheses. And if you want to see this as fraction, hit the fraction symbol over here on the left of the input bar, and you get 32 thirds. general, I like to have the upper in parentheses and also the lower in parentheses, because this negative here may need to distribute. But since the lower is a single expression, you can just write radical x. And since the upper has no coefficients, you can get rid of those parentheses safely. And technically, you can get rid of these brackets even because they're implied. And so we get for area 1, 32/3 is what we had in Desmos. And then, of course, this would be square units. And in a square unit, looking at this, each one of these would be a square unit. And we're saying that area 1 is 10 2/3. Area 2, also vertical strips. So we're going to integrate between x coordinates 4 and x coordinates 10. The upper function is now the radical. So it's radical x minus, the lower function is the blue. And the blue was the line 6 minus x. This is where you definitely must have parentheses because you're doing subtraction of multiple terms. You could also distribute the negative and just say minus 6 plus x. We're going to integrate from 4 up to 10. And we want to actually switch this around. I can put a plus in front of the radical, but a minus sign in front of the part we're being subtracted. That will work. And we get something that's approximately 21 3/4. Notice I don't have the option to turn this one into a fraction. That's because this time the answer is an irrational number. And so there's going to be some radical tens involved in our answer, which don't simplify to rational numbers. So if you want to get an exact answer to this, you're going to have to finish this out by hand. I'm just using Desmos to get an approximate answer, so I'm going to just go with approximate answers to speed this lecture up. And so we get an answer that's not equal. As soon as you approximate, you do a wavy equal sign. It's about 21.75 square units. Okay, now if we're after the total area then of all the gray, then we would just want to add these up. So A1 plus A2 would be approximately, when you decimalize everything, you get about 32.42 square units. Okay, I would leave it to you to try these integrals by hand and get answers and then compare your answers to what we're getting here with our decimal approximations. But I'll leave that to you on your own time. Let's look at the next example. Find the area of the region or regions bounded by the curves. Again, 4 curves are listed here. Purple is a horizontal line. That's the y equals 10. The blue, y equals 2x, is diagonal line. The red is the x equals sine of y, and then the green is a horizontal line at y equals 5. Now, in this particular problem, there could be lots of different regions that we think that we're after. Here, 2 horizontal lines are given, and then 2 other functions. So you really want to just be focused between the horizontal lines. In other words, don't be shading over here. We're not looking at that, nor these little slivers that you see here and here. That's not what we're after in this problem. We want to shade in between the horizontal lines and also between the curves that are given. Also notice that the red and the blue did not crisscross between the purple and green. So I don't need to do anything like I had to do up here and find a point of intersection. But definitely as I analyze this, I see that horizontal strips would be preferable, right? Because if I imagine a vertical strip, if you're to try to do vertical strips across this region and then add them all up, you have several complications. Let's look at it backwards. So going this way, we have purple minus blue. That's not a problem. But right here we have a transition. So now we have purple minus green. Purple minus green. Then here we get some issues. I see 2 different intersections. We've got this height there, we've got a second height here, and this really gets complicated in how to figure out how to do all these strips. However, a horizontal strip, if you integrate horizontally, or with respect to y, I'll say, it's always the right is blue and the left is always red, the whole way across up until the purple line. So I'm going to be able to do this in one integral, one clean integral, but I'm going to want to use horizontal strips and do blue minus red, do right minus left. This area here is going to be an integral. Everything is going to be in terms of y because I'm doing horizontal strips. We're going from a y coordinate of 5 up to a y coordinate of 10. And I want to do a function of y minus another function of y, and then dy. And the f of y needs to be the blue. That's the one that's on the right. The g function in my notation here needs to be the function on the left, which is the red. You need to find ways to express those in terms of x equals a function of y. Now notice that the red, that's already done for us. X is already written as a function of y. But the blue, that is not yet done for us. And so you have to rewrite this blue. Solve it for x is how you do this, because you get x is equal to y halves. You know, these are the exact same curve. They make the same shape. They're just one is solved for y and the other is solved for x. You just have to know which one you want to use in your setup. Now, because we're doing horizontal strips, you want to express everything as functions of y. My integral will go from 5 to 10. And my f of y is the y halves minus, and then the g of y is just sine of y, and then the dy. Let's go ahead and finish this one by hand. The antiderivative of y over 2 is y squared and then over 4. And the antiderivative of negative sine y is positive cosine y. And then we evaluate this from 5 to 10. So we get 10 squared divided by 4, that's going to be 25, plus cosine of 10. When you're doing this in using a calculator, make sure you're in radians, not degrees. Minus, and then parentheses, now plug in the 5. We have 25 fourths plus cosine of 5. You could change this back to 100 fourths so that you can subtract the 25 fourths, and you get 75 fourths plus cosine of 10, make sure you're in radians, and then minus cosine of 5. Don't forget this negative needs to distribute. And then if you go ahead and reach for the calculator now, you're going to get an answer that's approximately 17.627 square units. This should be a reasonable answer you get here. I mean, if you look back at this image and you start doing your best at counting how many of these squares there are, noticing that there's portions of them along the way, but you should be able to reason that 17 is a reasonable answer here. Okay, let's just do one more slide for this unit. Find the area of the region or regions bounded by the curves. We have a total of 4 curves given again. And this time there's a vertical line, and I do see 2 horizontal lines. Then I have y equals natural log of x, which is the blue curve. 2 ways to do this. First, do this by recognizing that ideally I think horizontal strips are ideal, because if you do a horizontal strip and you imagine the strip going across the region, first of all, before I do that, I think it's safe to say that the region that we're after is this one here. This is the only region that's bounded by the 4 curves. If I do horizontal strips, you start with the purple and then horizontal strips all the way up to the red. Notice that it's always the blue on the right and always the green on the left. So I can do a single integral if I do everything in horizontal strips. So let's do that first. Horizontal strips mean that the area is going to be an integral from one y coordinate to another y coordinate. So the purple line is y equals 0 and the red line is y equals 2. And then we do right minus left. But we have to write the right curve as a function of y. Right? So right now the blue curve is written as y equals natural log of x. We want to solve that for x. So just a brief review, if a natural log is the same thing as doing a log base e, and then if you write this in exponential form, you take the base, you raise it to that side, and it's equal to the argument of the log. So it would be e to the y is equal to x. And so we're going to have x equals e to the y is the right curve, and the left curve is x equals 0. So when I set this up, I do right minus left. The right is e to the y minus the left of 0, and then dy. Now, look at the consistency, right? Everything is y's when you're doing horizontal strips. The y coordinate to a y coordinate, a function of y and a function of y. Well, potentially a constant, right? And then a differential of y. This turns out to be a very simple integral. We'll just go ahead and finish this by hand. The integral of e to the y is just itself. Evaluate from 0 to 2, and so we get e squared minus e to the 0, which is 1. And we get e squared minus 1, which is approximately 6.389 square units. Okay, now this was probably the most efficient way to do this, but sometimes it's not so bad to do strips a different way. I'm going to look at vertical strips as a possibility for finding this area. So start with the green vertical line and then do vertical strips. Notice we're doing red minus purple up until we get to here, but then it switches to red minus blue up until red and blue intersect. The whole time across, the red is the upper function, but the lower function transitions from purple, transitions right here, and then goes to blue as the lower. So we're going to have to do this in 2 different integrals. We're going to find the green area first, right here. Then we're going to find the rest of it and then put them together. We'll do the green region and then the red region. Well, you'll notice that the green region is really a rectangle, so you could just do length times width on that green region and get an area of 2. Or you could do an integral to do it still and confirm that. Let's go ahead and do an integral. Let's say that we have area 1 and then area 2. Take care of area 1 first. Area 1 will be an integral. We're going to do vertical strips. We do need to figure out where these functions, purple and the blue, intersect, what x coordinate. The purple was y equals 0, and the blue is y equals natural log of x. To find out where those intersect, you simply solve natural log of x is equal to 0. In other words, whereas exponentiate both sides, right, there's the base e there, e raised to the 0 is equal to x. In other words, e to the 0 is 1. So we know that purple and the blue intersect when x is 1. We're also going to have to find out where there's the intersection of red and blue, way over here. So let's set red and blue equal to each other. The red is y equals 2, and the blue is y equals natural log of x. So set those equal to each other. Natural log of x equals to 2. Also exponentiate, we get e squared equals x, the x coordinate where the red and blue intersect each other. Okay, now let's go back and finish this out. Area 1, we're integrating from x equals 0 to x equals 1. So I'm doing vertical strips. Everything should be in terms of x. For area 1, the upper is a horizontal line, y equals 2, minus, and then the purple is the horizontal line, y equals 0. So it's a constant function of x and a constant function of x. And then we have the dx. This is just a 2 sitting in here. When you integrate 2, you get 2x, and then evaluate that from 0 to 1. Plug in 1, you get 2, and plug in 0, you get 0. We get 2 out of this. All right, we get a simple confirmation that the area 1 has area 2, which we could have known by just looking at it because it's a rectangle. Area 2, we're going to integrate from x equals 1 to x equals e squared. The upper function is still the constant 2, minus, but now we want to subtract the blue curve, but written as a function of x. Right, and the blue curve down below is y equals natural log of x. So when I'm doing area 2, I need to do upper minus lower, so I do 2 minus natural log of x, and then dx. All right, so this will be a little bit more involved to integrate. We're going to integrate the 2 part first. We get 2x minus, and then an antiderivative of natural log of x. This is one that we did using the table method when we did integration by parts. If you look back in your notes, you'll see that the antiderivative of natural log of x is going to be x natural log of x minus x. And then we're going to evaluate this from 1 to e squared. If you distribute this negative and combine some terms, this could make things a little bit easier before I do the evaluation. So we're going to have 2x plus x, we're going to have a 3x, and then minus an x natural log of x, evaluated from 1 to e squared. Now let's start plugging in e squared. We get 3e squared minus e squared times natural log of e squared, minus parentheses, we just get 3 minus natural log of 1. All right, let's do some simplifying. Natural log of e squared. That's like asking yourself, e raised to what power equals e squared? And the answer to that's 2. This right here is just equal to 2. So we wind up really having 3e squared minus 2e squared. That just gives me e squared. Natural log of 1 over here is 0, right? Because you would ask yourself, hey, e raised to what power equals 1? The answer to that question is 0. So we just get e squared minus 3. Now keep in mind that this is area 2. So when I actually now take the time to combine these to get the total area, area 1 plus area 2 is going to be the total area that I'm after. So it's going to be 2 plus e squared minus 3, combine the constants, and we wind up getting e squared minus 1. Right, the same thing we got up here. Now when you look at these 2 different approaches for this problem, it should be pretty obvious that the horizontal strips was the easier way to do this. You don't need to do both ways. I'm just showing you that often you can do these problems 2 different ways with horizontal or vertical strips, and sometimes they're equally difficult or equally easy. And that's it